Welcome to another video, and for today we are going to start answering problems using Kirchhoff's laws. And since this is our first time, we must first establish a sign convention rule that we must follow in order for us to correctly answer these problems and of course avoid confusions in the future. So for KCL, or Kirchhoff's current law, it states that the algebraic sum of the currents at any junction of an electric circuit is zero. Note that KCL always involves a node and the direction of a current flow, okay? So to illustrate, the rule is current entering is positive and current leaving is negative, and these are all equal to zero, okay? Now the second law is KVL, or Kirchhoff's voltage law, which states that the algebraic sum of the voltages and the resistance voltages in any continuous path of an electric circuit is zero. So first, if we notice a positive sign next to an element, for example, a resistor or a volt source, it means that there is a potential rise or current is entering in that polarity. Otherwise, the negative sign means that there is a potential drop or current is leaving in that polarity. So if, for example, we saw that this volt source has a positive sign here, we know by default that the current is flowing in this direction. And even if this element does not indicate the positive or negative polarities, we must already know that this side is positive because current enters here and leaves on the other side, which makes this a negative. And in writing down our sign conventions, we will choose the sign of the polarity we are going out of, not entering in. So let's say if we choose the clockwise direction, this value will be written as a negative because we left at the negative polarity. But if we choose the counterclockwise direction, we will write the value with a positive sign because we left at the positive polarity, okay? To make things more clear, let's go ahead and answer a simple problem. The figure shows a circuit in which two batteries A and B deliver current to a load resistor RL through line resistors RA and RB. For the values given, calculate the currents IA, IB, and IL, the load voltage VL, and the power PL delivered to the load. What I like to do first is to write the sign conventions in each element. In this case, we have resistors because it helps me to identify which sign I'm going to use in writing my equations. So let's go ahead and do that. Looking at VA, we know that the current is flowing in this direction because of the positive sign. So this means that in RA, this side is positive and this side is negative. Now looking at the other voltage VB, we know that the current flows in this direction because of this positive sign. And so the current in RB will enter in this side, so that's positive, and leaving at the other side, so that's negative. And lastly, for RL, or the load resistor, we'll have a positive sign here and a negative sign here. Alright, since now we have written the sign conventions, the next thing we are going to do is to identify the node we are going to work on, and also how many unknown variables we are going to find so that we can write our first equation. If we look closely at node E, we can notice that there are three currents involved, so we are going to use this. Remember that current entering is positive, current leaving is negative. So we write positive IA, positive IB, and negative IL all equal to 0. Or we can rewrite this as IL is equal to IA plus IB. So we have three unknown variables, therefore we need to also have three equations, and congratulations, this one is already counted as 1. So we have 2 more to go. This is where we are going to use KVL. And so we're going to put all the voltages in each element, but the catch is some of the voltages are unidentified, so we must use Ohm's law, which is V is equal to I times R. So for this, we are going to choose a loop that will involve all the unknown variables we are looking for as much as possible. So for starters, it's usually the biggest loop, and for this, we are going to follow loop ACE DBFA in a clockwise direction. So starting with VA, what do you think is the sign we're going to use? As I said earlier, we're going to write the sign in which we are exiting at, which is a positive since we are going in this direction, and we are leaving at the positive polarity. Now for this resistor, we are going to write V is equal to IR, so that's IA times RA. Now the sign is negative because we are leaving at this side of the resistor. Next we have RB. Again, V is equal to IR, so that's IB times RB. The sign we'll use will be positive because we are leaving at the positive side. And lastly, for VB, the sign we'll write is negative since we are leaving at this side. And these are all equal to 0. So now let's go ahead and substitute the given parameters. VA is 24, IA is unknown, but RA is equal to 0.4. IB is unknown, RB is 0.4, and VB is 26, all equal to 0. Simplify to find IB, we have IB is equal to IA plus 5. This is now our second equation. Just a quick recap, we already have the equation to find IL, and we also just made an equation for IB. So now we have to look for our last equation for IA. How? We need to find another loop that we can use. So let's trace loop ACEFA in a clockwise direction. Starting with VA with a positive sign. Again, this element will be written as IA times RA with a negative sign, and IL times RL with a negative sign because we are leaving at this side. Substituting what we know, we have positive 24 minus IA times 0.4 minus IL times 0.8, all equal to 0. Simplify and we'll get this as our third equation. Now let's do the math and substitute equation 2 to equation 3, and we'll get the current IA as 10 amps. Now we can use this to solve for IB using the second equation, and we'll get 15 amps. Lastly, for IL, from our first equation, IL is equal to IA plus IB, we'll get 25 amps. Now for letter B, we are asked to find the load voltage VL, and notice that IL is already known, and so we have the option to just simply use Ohm's law there, but since we are practicing Kirchhoff's laws, let's just pretend for a second that we don't have that information, okay? And so we are going to use KVL for this. The loop we'll trace should involve this part of the circuit, so it's safe to use ACEFA in a clockwise direction. Starting at VA, that's positive, IA times RA is again negative, and at this part we are now going to write VL because this is the variable that we are solving for. Now VL is a negative since we are leaving at the negative polarity. Substituting what we know, and we'll get the final answer of 20 volts. Finally, for letter C, we have to find the power delivered to the load PL. From the power formula, P is equal to IV, or current times voltage, which is 20 times 25, and we'll get the answer of 500 watts.